Yeah. Just say one or two words about myself, just to put myself in a little bit of context. So I mathematician, but I also am mostly a probability theorist. So I'm coming from to optimization from a different point of view, and I don't have a very deep understanding of optimization theory. I wouldn't claim to in front of you. I'm sure there's people here with much better understanding than me. But I am going to present something which I think maybe is still interesting and has a different set of hypotheses that are typically in optimization, and you can get some different types of results. There's a lot of people, some of them in this room, who this is based off of. The work is based off of, and so some at McGill. So Elizabeth Collins Woodfin, who's here, postdoc at McGill, and Inbar Sarusi, who is also a postdoc at Mila. She'll be around a bunch during the summer. Talk to her. Courtney Paquette, who's a professor. Maybe you'll know her, and some people from Google, from DeepMind, Ben Adlam, Jeffrey Pennington, and Lachau. Okay, so let me just start with what this talk is sort of not about. So the absolute, most textbook, as I understand it, optimization theory is based around this problem setup, where you would like to minimize a strongly convex smooth function, and it's maybe stochastic, and that will be what I'm going to talk about today. Everything will be stochastic. So I'm going to have some loss function L, and I'm taking some data X, and I'm taking the expected loss of some sort of parametric problem fitting theta. And then you have a very basic version of SGD that you can run, which is just this theta k plus 1 is theta k minus an update. And by the way, I'm mostly just going to talk about the one pass case today. So that's always going to be that I resample a new piece of data every time I run an update. And then what you can see is that in the nicest case, in the interpolating case, that you have this type of linear convergence. It's a very pleasant theorem. You have proved it for yourself. It's just like so buttery smooth that you get this nice linear contraction of the loss. And one of the things that I want to say is, I know that there's maybe it's just kind of an armchair discussion in optimization theory with regards to machine learning about which of these two assumptions is more wrong. Is the mu wrong? Is it really, like, real world problems are not convex? You should remove the mu. Or is the smoothness wrong? Maybe you have to remove the smoothness. You need to use non-smooth techniques. And I'm going to present maybe an alternative to that, which is that both of them are fine, but there's so many extra directions of optimization that you're looking at that they're not useful. So this sort of mental model of a single curvature bound above and below just leaves out a lot of interesting stuff. And so everything I'm going to do today takes place in between. So where you have nice models, but there's lots of directions. So kind of a motivating example is just going to be this one. In a sense, everything I'm talking about is just trying to understand this least squares problem. It's a classification problem built out of random features. I have built out of CFAR with random features. Just taking the CFAR data set and multiplying it by a Gaussian matrix, applying a CAN-H activation function, and then I'm trying to minimize the second layer. And just in context, if you look at the mu and the L that you get for this problem, well, that's the Hessian spectrum there. The ratio of the top to the bottom is about 10 to the minus 6. You actually have this beautiful plot also. But 10 to the minus 6 is just, it's way off. Like, it doesn't somehow reflect what, anything interesting about the problem. So if you run this for 10 to the 4th iterations, you start to see most of the optimization has occurred. So that's the training loss over different sizes of test set that we took. So 10 to the 6 isn't the right number. So 10 to the 4th is maybe closer to the right number if you wanted to just put two curvature numbers in there, some mu and some L. But actually, where does 10 to the 4th come from? Like, why is that an important number? I would love to hear a really convincing reason why that's the right number. for the amount of optimization that's happening, or the amount of steps you need to take in order for this problem to start to relax. Okay, so I just put a few more figures. I mean, this is the population risk in this simple problem. It's the same sort of picture. You have the same around the same number of steps where something happens. If you tried to threshold the eigenvalues just for fun, like what eigenvalues, if you wanted to imagine that, okay, some eigenvalues are just unimportant, I'm going to throw them away. Like which eigenvalues would you need to throw away in order to match what you saw in that picture? It'd be something like this, but it's a little bit arbitrary. And I think that finally, this is not a good idea to try to do that. It just doesn't really mean anything. So is there a better picture? Well, actually, the histogram of eigenvalues is not particularly revealing, but if you just look at a scatter plot of the eigenvalues of that problem, and you put them on a log scale here, what you see is a very appealing, basically straight line. So I put 3 figures up there. The version of this where I don't put any activation function, and that's in blue. And then I have the version in green, which is where I put the tan H, and then the red line, which is just a fit of that. And there's a nice straight line slope. So when you have this kind of straight line density, let's see, is mislabeled. That's just the magnitude of the eigenvalue should be on the y-axis there. So you have this other structure that appears there, which is this nice power law structure. Power law referring to the fact that it's a straight line on a log-log plot, and that you can use to do something. And so here's what I want to talk about. First of all, I'm going to tell you how to take that data that I showed you in the previous slides, this power law fit on a log-log plot, and turn it into loss curves. And I really want to know what is the loss curve that I see in running SGD, given an input, which is that eigenvalue data. The second thing I want to do is I want to do a really brief discussion of how random matrix theory works and how these log-log plot, power law eigenvalues get transformed when I do applications of random matrices to it. And then the final part, I want to take this stuff that I've discussed with power law eigenvalues and a little bit of random matrix theory, and use it to discuss a type of problem you can solve where I make a very, very simplified idea, a very, very simplified model of scaling laws. So where I choose a model size of a given number of parameters for a given problem, and then try to optimize it, and then really figure out in this simple model, given a fixed amount of compute, what is the right model size to pick, and what are the implications of some of the hyperparameters that we have, or some of the model parameters. So that's the plan. That's the plan. I'm going to give a little bit of discussion of loss curves, a little bit of random matrices, and then something about scaling laws. Okay. The first thing, and really this is in part to be able to do the last part. How do I give you an actual, basically a formula for a loss curve in some of these settings? And I want to start with something very, very simple, and there's a lot that we can do with this, which is going to be the following problem. So it's going to be a Gaussian linear least squares problem. Ultra simple. W is going to be a fixed matrix that appears here, and maybe that's a little bit unusual. I'm introducing it now to make sense later in the scaling law part. But what it's going to be is that, well, we want to minimize this linear problem. X is coming from some distribution. It's normally distributed some covariance matrix. The covariance matrix will eventually be a power law, but for the moment it could be arbitrary. And as optimizers in this setup, I want to imagine we don't have access to the actual data. The actual data is filtered through some matrix W. It will eventually be a random matrix, but it could be anything at the moment. And then we fit some linear underlying model to it. And the algorithm I'll use is just streaming SGD with a fixed step size. Okay, so it turns out that there's a formula you can compute for the expected risk as a function of time, and this actually uses the Gaussian structure. Just something I want to come back to because maybe Gaussian things are not something we want to assume. But okay, if you define this function psi of k to be the expected risk after k steps, then it solves this equation. Psi of k is a convolution equation. It's psi of k is an underlying f of k plus k convolved with psi. And you can view this a little bit like a bias variance decomposition. So f of k is some kind of underlying gradient descent problem, loss curve. K represents noise. What it actually is k, sorry, I'm way overusing the letter k. So that's k at k. K at k is the loss that you would see if you took 1 unit of gradient noise and then let it solve over k steps. So its magnitude and risk will shrink. And k of k is that curve. And what this equation means is that at every step of time, you have an underlying problem, which is solving. You make a small bit of gradient noise, make a mistake because you're doing stochastic gradient descent. And because it's a linear problem, that just is independent and flows to 0 at some rate. And that's the role of the convolution. So at every step, you generate a piece of noise and it starts decaying. This actually uses that this is a Gaussian problem. This is not an equality for general streaming SGD, but it is for Gaussian data. I wrote the formulas. I almost just want to just skip through it, but if you want to see formulas, this is what happens. You have to compute some sort of powers of a matrix. A is this I minus 2 gamma k hat plus 2 gamma squared k hat. You raise it to some power, and then f of k is, well, it should be interpreted as some kind of loss risk under the mean gradient descent, the mean SGD, and k of k is some noise term. Okay. Let me say a word about convergence behavior because it'll be important going forward. In this situation, you can say precisely when this algorithm is convergent, the full range of gammas. You need 2 conditions. The first is that this matrix has an operator norm less than 1. And so this matrix appears in the previous slides as a power. If it has an operator norm bigger than 1, this thing blows up. So that's a problem. So it needs to have an operator norm less than 1. The second thing, which is maybe more subtle, so the first thing looks a lot like, convergence criteria for gradient methods. And the second one is really a stochastic thing. It's basically some kind of second moment criterion that the magnitude of the noise is not too big. And this can be written as a trace. So gamma over 2, the trace of k over 1 minus k is less than 1. You can also characterize the limit loss here. The limit loss is precisely the limit of the underlying gradient descent problem, which is actually the minimal risk. And then you have an additional sort of effect due to using constant step size SGD. So it's a little bit worse than using constant. It's a little bit worse than just using than actually getting the argument of the risk, because you also have this 1 over 1 minus norm k term. Questions? Yeah, the box.
Yeah, so quick question, can you quickly recall me what are gamma and k hat? So I suppose gamma is the step size.
Yeah, sorry, gamma is the step size. R is the risk. I think maybe it's expected risk. Maybe I forgot an expectation. There should be an expectation. Or did I define it with an expectation?
Correctly defined.
Correctly defined. Well, here I put an expectation. So It is the population risk. It is an expected risk.
So K hat is the expected risk. Okay.
No, K hat.
R is the
K hat's different. What is K hat?
K hat is the covariance of the data, the observed data. So
Like
did I
an
write-
empirical covariance. somehow.
yeah, so you have an underlying population covariance K, and then it gets hit by a W. So there's a W involved. It's W transpose W, and then K is on both sides.
Okay, thank you.
Yeah, thank you. Very good.
K hat.
That was your question. Sorry about that. Yeah, it's another one, another K.
I know.
And so like 5 Ks now.
So here you will basically give like conditions over the step size to ensure convergence of basically the equation, and which means also of SGD.
Yeah,
Okay,
exactly.
And if K hat is, if W is random,
At the moment, I'm just taking W as a fixed matrix. I will take it random in a moment. I'm conditioning on it. It's not, I'm not averaging over it or anything.
Thank you.
Okay. So I want to just make a small detour. So I'm going to talk about scaling laws, but I want to give a small detour about a particular case, which is nice because you can say more things here. And that's the high dimensional case. And what do I mean by high dimensional case? So I want to be precise. So you can measure the intrinsic dimension of the problem by comparing the operator norm of the covariance to the trace of the covariance. So when the trace of the covariance is much, much bigger than the operator norm of the covariance, it's got lots of directions. It's not just one dimension. When that's true, a couple things simplify in this case. The first thing is that the convergence criteria just becomes about the trace. So the operator norm condition disappears. It's masked by the trace condition. The convergence just turns into a question about whether the trace of the covariance times gamma over 2 is less than 1. That's just because the other one is much easier to satisfy than this one. A second thing which you can observe, and which I have some theorems to share about in a second, is that the loss curve actually concentrates. R was not the expected risk. R is the actual risk, and actually the curve as you vary K concentrates around some deterministic curve. So you would actually observe in single runs of SGD a single loss curve. So the thing that happens, and that's also occurring in the high dimensional case. The Volterra model simplifies. You can replace some of these I minus things by exponentials. You have a slightly simpler set of formulas that occurs in the high dimensional case. The other thing is that the data distribution becomes unimportant in the high dimensional case. So you can replace Gaussian data by general data with some assumptions, and you get the same theorem. So the exact same loss curve holds up to an error, which has to do with how good that approximation is, how much better trace K is than operator norm K. So here's the theorem. This is with Collins-Woodfin. So we're streaming SGD on linear regression, basically everything I said. So the risk minus psi of K is small by some power of D. D is the dimension. And you need some assumptions on the data, so various things that make it look a little bit Gaussianish. It doesn't have to be Gaussian, but it has to have some features that Gaussian data would have. I maybe just take one other detour and say, I've talked everything about linear problems. There is a version of this that you can do outside of the settings I said. So you can remove the streaming assumption. You can look at multipass SGD. You need more assumptions. And you can also do this outside of a linear regression setting, but the actual loss curve description becomes more complicated. So instead of having a Volterra equation, it becomes some sort of more complicated set of ODEs that you have to solve. But there are descriptions of this that you can do outside of a linear loss, of a quadratic problem case. Okay. So just want to summarize. First part of this talk was that there's a way to take data about the problem, the eigenvectors, the eigenvalues of the problem. You put them into this convolution Volterra machine that was this loss curve model, and out comes curves that describe the risk of the problem over time. What I'd like to do now is say a little bit about the eigenvalues that you see and where, say, this kind of histogram comes from. So that comes from taking some data, applying some random matrix to it, and then getting whatever that is. This beautiful wave. So I don't want to go too much into random matrix theory. I know this is probably not your, maybe it's your cup of tea. I don't know. I come from random matrix theory, so I'm really excited about it. But I'll spend a few minutes, just a few minutes to talk about random matrix theory because there's a few ideas I need. And to be not too complicated, I'm just going to talk about the linear case. So I want to imagine that I have a covariance matrix K. That's a population covariance matrix. And then I do this filtering operation on it. So I take my underlying data and I multiply it by a matrix W. And I observe some covariance matrix K hat. So K hat is the observed covariance of the data, comes to my optimizer. And I want to now consider what happens when W is random. So if W itself is a random matrix, which represents somehow that the underlying data is being filtered randomly, effectively, and I get something else. Okay, so W is going to be, that's just notation for a V by D matrix of IID, normal random variables, variance 1 over D. It's possible, it's possible like someone could do it, look to prove things about the nonlinear version of this where you put activation functions. I have nothing to say about that. I think it's an interesting math problem, and I think it's a great thing to do in terms of ways of extending things that I'm talking about. Okay, so this curve you maybe seen once before. This is the case when my underlying covariance matrix K, population covariance matrix, is the identity. So I take the identity, and then I'm making this W transpose W operation. So my K hat is just, or in fact, W transpose. And if you go, it's a very easy simulation to do. You can compute the eigenvalues of this. You see some really beautiful analytic looking curve. It's called the Marchenko-Pasteur law. There's a density there. There's actually a formula for that curve. There's also, maybe more relevant for us, some sort of characterization of this orange line, this density, which is not explicit, which I will tell you in a second. Now, the way I want to push this is I want to look at situations where the covariance K has some kind of shape to it. And so I'm going to just start that. This is A is equal to 0.1. So I take K to be diagonal J to the minus alpha. So it has some kind of eigenvalues J to the minus alpha. If W was not so rotationally invariant, it would matter that it was not a diagonal matrix, or if it was a diagonal matrix. But here, because it's Gaussian on the inside, I just can make K diagonal. It's the same as taking a matrix K with some eigenvalues, which are J to the minus alpha. Okay, but anyway, I get some other curve. Looks pretty similar. I mean, after all, this is a D is 4,000 and alpha is 0.1. So basically just put ones there. As you change this, you see a more distinct picture. So something's happening. So you get these other curves. And the only thing I'm trying to illustrate here, first of all, is that this is a log eigenvalue on the bottom, log base 10. So these are quite small eigenvalues. It's like 10 to the minus 6. And that's the same size of matrix. So it's a 4,000 by 4,000 matrix. But there is some sort of analytic theory, which I'm going to describe in a second, which actually tells you what this eigenvalue density is. It's a way to access it. And also, I'm not going to prove anything about this, but I hope it looks at least somewhat reminiscent of what you saw in the CFAR situation, where I did the same thing. And I don't know, at a look test, it has similar hump shape. Okay. Probably the more relevant feature is this one, which is that if you do the scatter plot of the eigenvalues, you do see a power law. So the ith eigenvalue here looks like I to some power. And the power is actually the same power as comes in to the model. So if I take diagonal covariance, the j to the minus 2 alpha as its eigenvalue, and I go in and I do this random matrix transformation and then observe the eigenvalues, I basically get the same thing back. There's some small distortions, and they are relevant for numerical simulations. For example, at the top, j to the minus 0.2 is not quite on top of each, quite a straight line. Just one word about random matrix theory. Mostly random matrix theory is done by considering this function, the resolvent. So you take the random matrix you're interested in, KW, W transpose K, you subtract a complex number Z minus the identity, you take the inverse matrix. This is a random matrix valued function. This has eigenvalue, it has poles, and when at real numbers Z, which are the eigenvalues. If you're off of the real line, this is a good function. You can compute this inverse. And random matrix theory basically tells you what that thing should be. So there's a deterministic equivalent for the resolvent. What does that let you do? Well, if you have some expression that you can write in terms of a random matrix, if you have something that depends on a random matrix, and you re-express it as something that depends on the resolvent, and you can replace the resolvent by the deterministic equivalent, and now you know a deterministic rule for how the expression behaves. What is the deterministic equivalent? Well, in this case, there is a fixed point equation you can solve. So the resolvent looks like some diagonal matrix. K was diagonal. So the off-diagonal parts of the resolvent turned out to be very small. And M, which appears inside, is the solution of some equation. So M solves the second equation. M of Z is this reciprocal. This may look like a useless equation. I promise it is a useful equation, and it's useful in two ways. The first is that you can numerically solve it. So if you want to numerically evaluate things, like in the pictures I showed before, you can numerically solve for this fixed point equation. You have your M, you're off to the races. The other thing is that you can analyze it, but you have to have basically a good guess for what M is. If you have a good guess for what M is, then you can check that it approximately solves the fixed point equation. If it approximately solves the fixed point equation, you can prove that it's actually close to the true solution. So with some intuition, you can then use this to prove things about M. This slide, I think, says everything I just said, but in lots of text. So same thing. That's random matrix theory in one slide. Okay, so that's the picture. So I've told you a little bit now of how you can take deterministic problems and look at, well, rules for evaluating the eigenvalues of a random matrix like this. Okay, scaling laws, the final part of this talk. All right. Now I'm going to be over my skis. Okay, so that's the abstract of the GPT-4 technical report. I'm only going to look at one sentence, this sentence. So a core component of this project was developing infrastructure and optimization methods that behave predictably across a wide range of scales. This allowed us to accurately predict some aspects of GPT-4's performance based on models trained with no more than 1/1000th the compute of GPT-4. Okay. And I wasn't competent enough to read this sentence myself, so the Xiao told me about the sentence. Then I went and read it. The point of this is, and I guess if you're working on scaling laws, you don't need to hear this from me, that, well, you can ideally understand smaller models in great detail. And then when you go to train larger models, if you understand correctly how to grow the parameters, how to change the hyperparameters, all the bazillion hyperparameters you have, then you can do a good job of training the large models. And moreover, you kind of have to do that because you don't have the ability to grid search over the hyperparameters of the big model. So you really need to know and have opinions on how the problem changes as you scale it. And I'm going to also add another point of view here. If you're doing this type of scaling law, you're probably in the compute limited type of scaling law, which is to say you have all the data in the world, acquired legally or otherwise, and you do not have all the compute in the world, though you're spending lots of money to try to get all the compute in the world. And what will finally limit the training of your model is how many floating point operations you can finally do on it. So for a given amount of floating point operations and unlimited data, what's the right thing to do? So now, to make this very specific, I'm going to give an analysis of a very simple scaling law problem, which is motivated by that setting. So I'm going to suppose we have this latent data vector x. We embed the random vector in dimension RD, so there's an ambient dimension V, and I should imagine V as being much, much bigger than D. And I embed it in dimension D by applying a random matrix to it. This is my extremely simplified model of what it means to do all of machine learning. You take data and you transform it by some sort of representation into a d-dimensional problem that you then optimize over. So D is the number of parameters that you have to work with. We're trying to predict a linear model. It's just going to be a x inner product beta hat. And so we don't have access to x, but we have observations of x beta hat. And beta hat is some vector. And then we're going to train it with streaming SGD. And the important point to note is that we have to compute gradients of this. So every time we run a step of SGD, we have to compute one dot product that computes that costs D units of flops. And so the question is how to choose D now. If I choose D too big, I've paid way too much because every dot product is hugely expensive. So if I choose D too small, I'm losing so much information by doing W transpose X that I lose that way. So there should be some sort of middle ground, how to choose D for a given number of flops in order to do the best possible. Okay, so this is a more formal version of all of that. So I'm going to take psi, which is the solution of my loss curve. I have a formula for my loss curve. It solves a convolution Volterra equation. It's psi. It depends on the number of steps. Now here, F is flops. I've divided flops by D, so that corresponds to the number of steps of SGD that I take. D and V are the scales, the model parameters. I'm thinking of V as basically being infinity, or I want to, but it's not something I would choose. I choose D. And then alpha and beta are two parameters which are related to the setup here. So psi is the loss. Xj, that's going to be the data. So the data is normally distributed with variance j to the minus 2 alpha, and that's independent over j. And beta hat is some other j to the minus beta, and that's, I say independent over j, it's just deterministic. It's beta hat j is j to the minus beta. V, I want to be much bigger than D, though it actually sort of depends on what alpha and beta are. If alpha is less than a half, then the sum of squares of the xj's is finite, regardless of what V is. So I can think of V as being infinity. Otherwise, I have to do other things. And actually, to be concrete, I'm just going to take V and D proportional throughout all this. So V will always be a fixed multiple of D, that way. And I'm going to run streaming SGD. This has appeared under the language, the neural scaling law model, simple neural scaling law model, probably most significantly by Maloney, Roberts, and Sully, who were actually in Montreal, I think, when they did this. Maybe some of you know them, I don't know, yeah, but they introduced this model, but they were not considering it as a compute problem. They were considering it just at time, basically infinity. So you can run it as long as you want, and they're optimizing for the amount of data. So slightly different problem. So here I have infinite data. And there's also recent work of Bordelon, Atanasov, Pehlevan, where basically they do this, but they don't use SGD, they use essentially gradient flow. So it's not quite a compute limited, it's something else. Okay, what to say about this? First thing, this psi, which is appearing here, that's the risk. Psi is a complicated thing. It solves an equation. But what can you do with psi? Well, it turns out that actually in this case, you can drastically simplify psi. You don't have to solve this equation. So psi is a solution of psi is f plus k star psi. It turns out because everything decays so slowly, this type of Volterra equation simplifies in structure. So instead of solving f plus k star psi, you can solve f plus k star f. And that's a good approximation for psi, up to constants. That's a lot easier because it's not solving an equation. You just have to compute one convolution. So now you're accurately approximating psi. So for the purpose of understanding up to constants the behavior of the loss curve, we can just look at this. Second thing is that the underlying functions simplify a lot. I think maybe I want to, okay, well, I'm going to introduce these things, but f, the forcing function can be brought down to 3 parts. And sometimes you don't have all 3 parts. So the forcing function, that's the loss of the underlying gradient descent. Can be broken into 3 parts. An f0, which is a constant, which has to do with the fact that you don't actually contain the target in the span of your model. The target was beta inner product x, and you have a W filtering matrix, which unfortunately means you don't actually have beta in your target. So there's some amount of residual error, but the minimum loss that you could achieve, and that's f0. FPP is going to be, that's PP is for pure point, is the gradient descent on the largest eigenvalues. So the largest eigenvalues tend to carry most of the information. You can sort of work out what the gradient descent is on them. It has a nice formula, and this is the loss of the gradient descent part. And then finally, there's an FAC, which is a little bit enigmatic. I think would be easy to miss. And in words, it corresponds to the fact that your largest features, most heavy features, that is the ones with the largest variance in the covariance matrix, they get hit by this matrix W, and they no longer are exactly aligned with coordinate axes. So the first eigenvector, which gets sort of spread. And so there's a little part of it, which varies with dimension, which is spread out over all the spectrum. If you like, it's the fact that your embedding didn't do a good job of preserving the largest features. So the most dominant features were slightly distorted by your embedding, and you can still measure the loss curve, the contribution to the loss curve of actually fitting those parts. And that's FAC. And then finally, there's KPP, which is well, it turns out to be just what K is, this contribution of SGD noise. Okay, so it's a lot to keep in mind. I know I'm probably going to give you a figure here in a second. The other thing to say is that everything here behaves in this power law fashion. So all of these curves are up to constants, some inverse power of K to some power of D. Yes, please.
Yes, quick question. So it's for F0. So since you take a random matrix and if you take it square, it should be technically invertible. So F0 should be 0 most of the time, or you purposely make thinner matrices and therefore F0 won't be 0 in that case.
Yeah, so the dimensions are such that you do not have W transpose W invertible. It's the other symmetrization. So there is a kernel, but it's actually quite small because the vector beta is mostly concentrated in large directions, which is faithfully like isometrically mapped by W. So like F0 is going to go to 0 as an inverse power D. So little bit, and it has to do with, so V is bigger than D is finally what the reason was.
Okay, thank you.
Okay. Okay. what's the answer? Okay, so what is this picture? I just showed you this wild picture. So it turns out that there's a whole bunch of behaviors that can get out of this. And I want to talk about a little bit of each of these parts. This is a phase diagram of different regions of the loss curves. So, and furthermore, what the compute optimal behavior is. So the compute optimal behavior is different in each of these patches of alpha beta. So the y-axis is the alpha line, and small alpha at the bottom and small beta at the bottom. We count here sort of three parts, which we're calling phase one. Those are kind of the boring ones. I'll explain why. And then phases 2, 3, and 4, which each have their own sort of trade-offs. And then there's some sort of amazing point in the middle that intersects all of them, which is when alpha and beta are 1/2, which is really magical. And if you can tell me a natural reason why that's the most important case, that's really cool, because it's also the one which is all the math. So everything in principle is happening at that point, and we don't have any theorems about it. So that's probably a really nice probability problem to understand what happens there. But okay, let me talk a little bit about this. By the way, I'm talking about complexity on the top and the bottom. You can view alpha as an inverse complexity problem in the sense of if you wanted to approximate a sample from my underlying data distribution with some number of bits, how many bits would I need to approximate it up to an error epsilon? So higher complexity in the terms of the number of bits is lower. And so it's the low complexity things which have sort of different behavior, 2, 3, and 4. And the same thing for beta. How well do I need to approximate them? How easy it is to approximate them. So there's the phase one. Phase one is really simple. Phase one is what that's like the phase where stochastic optimization is completely irrelevant, and all that's happening is you have gradient descent on the outlier eigenvalues, which are not affected by the random matrices, and the stochasticity plays no role. And what happens? The loss curves look like this diagram up here. They come down on some log plot in a straight line. You can figure out what that rate is. And then they saturate at some point when the limiting loss comes into play. It turns out that if you want to figure out the best D to use, so if you want to optimize this now over D, then basically the right thing to do is to tune the number of flops so this corner appears where you want to stop. So you train the model to completion. That is, you train the model all the way till you get minimal loss. And then you make the model big enough so that that regime of training completes exactly at the number of flops that you care about. And that's the right thing to do. You can work out what those are. It depends a little bit on what regime, what the exact formula is for the number of flops. That is the dimension, how to pick it in terms of the number of flops. But this is where basically where you run optimization to completion, and you should take the biggest model possible to do that. It sounds intuitive, right? Like that's the right thing to do. Usually that would be the naive thing to do. But other things can happen. So phase two, this region up here. So this is the region where alpha is bigger than beta. So if you like, alpha is bigger than beta means you have a more complicated target than your data. Maybe an unusual situation, maybe not. Well, SGD noise still doesn't play a role here. That is to say, you can just view this as the underlying mean gradient descent problem. But if you run through where optimality occurs, it occurs where the trade-off between the pure point part of the loss curve intersects the absolutely continuous part of the loss. So you don't want to, in other words, in this regime, train the model to zero loss or to minimal loss. You should stop early. And you stop early when you start to get into the regime where you fit the hard features. So there's the easy features, which are well aligned. Your embedding did a good job on them. There's some range of bad features. And you stop at the region where you have the hard to optimize features. If you want to do a better job, you should improve your model. You should increase your model. There's a third phase, phase 3, where everything matters. So this is the regime. So that's the regime over there. That's a beta is bigger than alpha. Beta is bigger than alpha. Means you have a lower complexity target than your data. I think this to me makes the most sense. Your data has lots of information in it. Your target has less information in it. And you're trying to fit a lower information target using lots of data, lots of rich information in it. And here, SGD noise actually plays a role in the sense that it changes the way the loss curve operates. If you were looking for a region where using a different optimizer was helpful, this would be the region. So far, it didn't. All the great tricks that exist in optimization theory, I think probably would have done nothing. But here, there's probably something to be gained. The optimizer is slowing you down. And the trade-off occurs when, well, at this corner here, so this compute optimality occurs when the slowed loss due to SGD is overtaken by trying to learn the hard features. You still don't want to try to learn the hard features, apparently. There's one other interesting feature here. D star is f to the 1/2. So the correct number of parameters to pick is exactly square root the number of flops. And that has nothing to do with alpha and beta. This number, square root of f, appears in lots of places, not everywhere, but in lots of places in this computation. And I wonder if there's some deeper meaning to that. I don't know if you needed a baseline number of parameters to pick for a given number of flops, maybe it's d square root of f. And then finally, there's this phase 4. Phase 4 is different in a couple ways. It's below this alpha is 1/2 line. That's the region calling the high dimensional line. That's where the trace of the covariance is much, much larger than the operator number of the covariance. And again, SGD noise is important, at least for part of it, in that it slows down the optimization. And in fact, depending on where you are, there's phase 4A and phase 4B. It could be that you want to just soldier through and get through the part where the SGD noise slows you down, or maybe not. And again, this D star is f to the 1/2. Here's. I just close with maybe a picture. So I have just one picture prepared. This is the type of picture you see from this theory. So this is a couple different phases. This is just phases 1, 2, and 3 of running this. So these are loss curves with the superimposed results of the random matrix computation. And the theory curves are coming from, well, these 3 parts of the losses, FPP, FAC, F0. You take the max of them, and then you can also fit this compute optimal curve according to where those corners were. And I should emphasize, if you look carefully, there's not, these lines are not always right on top of each other, but our theory is only working up to multiplicative constants anyway. So there should be thought of this as a band. So there's some sort of band where the action is happening, not right on top. Okay. I think I don't have any more slides. This is where I stopped. There's a black slide at the end. I'd be happy to take any questions or discuss any of this with you. Thank you.
Okay, so we have approximately 10 minutes for questions. I do have one question, actually. In neural network, actually, we usually initialize all the weights at random, and it has been not really justified. So do you think that what you just showed using that random filtering matrices can justify the fact that we initialize all the weight at randoms, and that's why maybe it's working better also for reproducibility?
Well, it's a great question. Yeah. So first of all, I'm sorry that we don't have really a lot to say specifically about neural networks in this. I think it's super important. Yeah, and you can see it in when you do some analysis of SGD on, say, random features models or on shallow neural networks, that the optimization or that initializing at random is really important. And I think roughly, if you just wanted one reason, it's because you need enough samples sort of to boost your inner product with an unknown signal. You have some sort of low dimensional manifold of interesting signals, and you need to hit it with enough vectors to have a chance of capturing some proportional amount of the data. If it's randomized at 0, or if it's too thin, then you just don't have any of that in the span of your dot products. So random dot products are good in the sense that they behave like isometries. Like big random matrices are good because if you have a big random matrix, you multiply by something, you get an embedding of it. And that, yeah, and I think that there's a lot sort of to do in terms of random matrix theory of neural networks, showing how exactly that randomness is helpful. Yeah, but I think that's a big and interesting topic.
Thank you. Yes, Nicolas.
Thanks, Elliot. My question might be very naive, but I'm trying to understand. So you, maybe not in this slide, but on the previous one, I think you said something basically about the first part of the curve and the second part. Can you go back to the previous slide, maybe?
Yes.
I'm trying to see exactly the terms you used. Yes, you call them the distorted features.
Yeah.
So first, I maybe I would ask you to, if you can explicit what distorted features mean.
Yeah.
And then I'm also trying to understand, because you say you basically want to increase D until you use your entire compute budget at the end of the blue curve.
Mm-hmm.
Is your notion of distorted features also dependent on D?
Yeah.
So I'm trying to understand what exactly, aside from these curves, what exactly you learn with a bigger D and less compute compared to a smaller D and then you go too far. Does that make sense?
I think so. Let me give it a shot. So first of all, there's what is distorted features. Okay, so in the setup we had a population covariance matrix which was diagonal, and the first entry was the largest variance. It had the biggest weight. The basis that you should look at to analyze SGD is in the basis that diagonalizes the observed covariance matrix. So the observed covariance has a W in it, has a random matrix in it. So its eigenvectors are not coordinate vectors. First vector is not a coordinate vector. It's very close to being a coordinate vector. You can take the first vector of your observed matrix and your observed covariance matrix, and you can expand it in an eigenbasis, and you get that it's 99%, or actually 1 minus 1 over D or something like that, in the direction of the first one. There's an alignment of the actual eigenvectors and the underlying population covariance eigenvectors. But there's that fraction of 1 over D, and it gets spread out over the whole spectrum. So if you finally want to correctly solve just in the first coordinate, your linear model, so that you actually exactly match the first coordinate part, you would actually need to match, when you expand in the new basis, all the smaller directions. And they're very slow because their eigenvalues are much, much smaller, and it takes a lot more time. In these loss curves, there's a region which is dominated by doing that. That is, solving for the leading directions, the directions which are most important in the population covariance direction. The leading directions you have to are embedded in some weird way in the empirical covariance spectrum, and then you're actually solving the part of the problem which is coming from that. And it's slow because the eigenvalues are really small. The curvature is really small. And that's this FAC region. So that's what's dominating the loss curve here. And what happens in the compute optimality, and I don't know if I have a first principles reason why this has to be, but it never pays to solve for that part. You should always stop the optimization before that and instead increase your model size. So it's more compute, the better compute trade-off is just to use a bigger model and not worrying about trying to solve those hard directions, at least for using SGD. Not sure if that changes if you change optimizers, but.
So in the very first slide, you stated that we're thinking about the interpolating regime here.
Yeah.
And so following that, SGD can work with a constant step size, but in practice, especially in the type of models that are analyzed here, you'll typically have like a 1/time reduction. And a lot of that is, or mostly that is, to fight SGD noise as you get closer, ideally, to some solution. Given that you've talked a lot about how like in some of these phases, the noise is important and others is not, would this analysis be much different if you use like an inverse decay on your step size or something of that nature?
Yeah, it's a good question. So I think the first thing is that if you do that, I think that there are regions of these phases where you're, say in this one, where this first region is dominated or slowed down by SGD noise. And I think you probably might it may not be SGD noise anymore that dominates you. In this problem, there's a huge cost though to decreasing your step size, in that the amount of eventual loss you lose for a fixed step size here is a multiplicative constant loss, and we're going down orders of magnitude. So in this picture, the cost of using a fixed step size is some window of this F0 of some amount. So I think that if you did a side-by-side comparison of a decreasing step size and a constant step size on this problem, the constant step size would still win that. Now, it could be that there's other methods, which, I don't know, averaging or momentum things or other techniques for reducing variance, which also preserve this sort of constant step size thing, but actually take you out of a SGD noise dominated regime. And that would be cool to see. I don't know the answer to that at all.